Today we are going to learn about optimizing Keras sequential models for performance. This video will teach you essential skills to enhance model efficiency and accuracy using optimization techniques.
Welcome to this tutorial on optimizing Keras sequential models for performance. Optimization is crucial in the field of machine learning, ensuring that models run efficiently and produce accurate predictions. In this video, we'll explore various optimization techniques, from understanding batch sizes to fine-tuning pre-trained models. You'll learn how to apply these techniques to your models, ultimately improving both speed and accuracy. Whether you're dealing with large datasets or aiming to prevent overfitting, these strategies will provide a foundation for better model performance. Let's dive in and discover how to get the most out of your Keras models.
Batch size refers to the number of training examples utilized in one iteration. It's a critical factor that influences both the speed and accuracy of model training. A smaller batch size generally offers a more accurate estimate of the gradient, leading to potentially better model updates but at the cost of increased training time. Conversely, a larger batch size might speed up training but can lead to less accurate models if not balanced correctly. It's essential to experiment and find the optimal batch size that maximizes efficiency without sacrificing model accuracy. Consider your hardware limitations, as batch size also affects memory usage, particularly when dealing with large datasets. By understanding and adjusting your batch size, you can significantly impact the overall performance of your Keras model. Choosing the right optimizer is crucial for model performance. Optimizers adjust the learning rate and weight updates during training. The most common optimizers include stochastic gradient descent, SGD, ATOM, and RMSprop. SGD is straightforward but can be slow to converge. ATOM is popular due to its adaptive learning rate, which adjusts itself during training, often resulting in faster convergence. RMSprop is similar to ATOM, with a focus on adjusting the learning rate based on recent gradients. Each optimizer has its strengths and weaknesses, and the choice often depends on the specific needs of your model and dataset. Understanding how each optimizer works will help you make informed decisions, improving your model's speed and accuracy.
Learning rate schedules are strategies to adjust the learning rate during training, enhancing model stability and convergence speed. Common types include step decay, exponential decay, and reducing on plateau. Step decay decreases the learning rate at set intervals, while exponential decay reduces it continuously over time. Reducing on plateau involves lowering the learning rate when a metric stops improving. Implementing learning rate schedules in Keras is straightforward, using callbacks like learning rate scheduler or reducer on plateau. By tailoring the learning rate to the training dynamics, you can prevent overshooting minima and improve both speed and precision of convergence, ultimately leading to a more robust model. Overfitting occurs when a model learns the training data too well, capturing noise and details rather than the intended output. Regularization techniques like L1 and L2 add a penalty to the loss function, discouraging overly complex models. L1 regularization adds a penalty equal to the absolute value of the magnitude of coefficients, leading to sparse models. L2 regularization, also known as weight decay, penalizes the square of the magnitude, encouraging smaller weights. In Keras, you can implement these using the kernel_regularizer parameter and layers. Regularization helps your model generalize better to new data, but it's crucial to balance the strength of regularization to avoid underfitting.
Dropout layers are a popular technique to prevent overfitting by randomly dropping units during training. This prevents neural networks from becoming overly reliant on specific nodes, reducing the chance of co-adaptation. During training, dropout layers deactivate a random set of neurons, forcing the network to learn more robust features. In Keras, you can add a dropout layer to your model and specify the dropout rate, indicating the fraction of units to drop. While dropout can slow down training, it often leads to better generalization on unseen data. Remember to only apply dropout during training as it alters the network's behavior, and turn it off during evaluation for accurate performance assessment. Working with large datasets presents unique challenges, including memory constraints and longer training times. To handle these efficiently, consider using data augmentation to artificially expand your dataset with transformed versions of existing data, providing more variety. Batch processing techniques, such as mini-batch gradient descent, help manage memory usage by processing data in chunks. Keras offers data generators that allow for real-time data augmentation and efficient batch processing. For very large datasets, leveraging cloud resources provides scalable compute power, ensuring that training remains feasible. By employing these strategies, you can effectively manage large datasets, improving your model's training efficiency and performance. Callbacks are powerful tools in Keras that allow you to monitor and control the training process. They can be used for various purposes, such as early stopping, saving model checkpoints, and tracking training metrics. Early stopping halts training when a monitored metric stops improving, preventing overfitting. Model checkpoint saves model weights at specified intervals, ensuring you can recover the best version. You can also create custom callbacks to implement specific logic during training. By utilizing callbacks, you gain greater control over the training process, ensuring that your model achieves the best possible performance.
Fine-tuning pre-trained models, a process within transfer learning, involves adapting an existing model to a new task. This approach leverages the pre-trained model's learned features, which can significantly reduce training time and improve accuracy, especially with limited data. Start by selecting a model trained on a similar domain, like ImageNet. Freeze the initial layers to retain learned features and retrain the final layers on your dataset. Gradually unfreeze layers for further fine-tuning. This method not only enhances model accuracy but also efficiently utilizes computational resources, making it a valuable technique in modern machine learning workflows. In this video, we've explored various techniques for optimizing Keras sequential models for performance, from adjusting batch sizes to implementing learning rate schedules and fine-tuning pre-trained models. Remember, optimization is an iterative process, often requiring experimentation and adjustment to find what works best for your specific use case. Continue to learn and explore new techniques, applying your skills to real-world projects. Optimization not only improves model efficiency and accuracy but also empowers you to tackle more complex challenges. Thank you for joining us, and keep pushing the boundaries of what's possible with machine learning.